What's up, ladies and gentlemen? Today we'll be talking about metabolism and the energy systems. Let's get it popping. So, understand here, your body is lazy. Okay, and what I mean by lazy there is that it will do the very minimum to keep you alive there. Okay, for example, your heart won't beat any faster than it needs to. You won't pump more blood around your system than you have to. You won't breathe faster than you have to. Your muscles won't contract harder than they need to. You won't create and store more energy than your body needs to. Okay, because um, any arrangement of your body there, okay, in which more is needed to be done in order to survive there, okay, is very metabolically inefficient and therefore not very conducive to longer life. So basically, your body wants to do the bare minimum needed to be able to survive. Now, as we talked about previously, in order to perform work there, we need energy, because energy is defined again as our capacity to perform work. And work is defined as applying a force through some sort of distance. Therefore, anytime we want to perform any sort of movement, okay, or exercise or whatnot there, work must be performed, and therefore we need energy in order to fuel that work. So, what is this term metabolism here? So, essentially, it's the total of all the different chemical reactions there that occur within the cells. And oftentimes, metabolism can be classified into two different categories. Anabolic changes. Anabolic just means we're creating substances, okay? Basically, making larger molecules from smaller molecules. Versus catabolic is the exact opposite, taking larger molecules, breaking them down there. Okay? So anabolic, creating substances, essentially taking Lego pieces and putting them together. Versus catabolic, there is taking a larger piece and breaking off individual Lego block chunks. For our purposes here, it's oftentimes simpler, maybe, just to think of metabolism as the process by which we create energy. Okay, and specifically for us to think about it here is converting food from one form of energy into another form that will allow us to move. And we can oftentimes also term this as bioenergetics. Bio meaning living organism, energetics meaning energy. So the process of living organisms to create energy by converting food from one form of energy into actual movement, another form of energy. Here's something we've seen previously in this semester here. We got various forms of energy. Could have chemical energy, mechanical, heat, light, electrical, and nuclear. Okay, and certain forms of these energy are used in our body. As we talked about before, energy can be converted from one form in that previous slide to another. Okay, exercise requires converting chemical energy into mechanical energy, because food enters our body, okay, as a form of chemical energy, okay, and then we convert that food into a certain substance, okay, certain format there that our body can use to fuel movement there in the form of mechanical energy, essentially turning food into exercise. So with our food entering our body there, okay, it is in the form of chemical energy. And there's three main macronutrients, okay, that our body uses to create energy. There will be a fourth one that we'll briefly mention later on in this PowerPoint slide set. But essentially there, we got three main sources of energy there in our food. We've got carbohydrates, fats, and proteins. And we'll go into more depth into each of these sources later on in this PowerPoint slide set. Okay. Unfortunately, food itself cannot be converted directly into mechanical energy. Okay. So it's not like it can take carbohydrates there and boom, immediately use it as energy. Okay. What we need to do first is take these carbohydrates, fats, and proteins, okay, and we need to change it into a chemical energy format of adenosine triphosphate, oftentimes abbreviated as ATP, adenosine triphosphate. Okay, Essentially, we think of adenosine triphosphate there is the currency of our body. Okay? Just like in the United States here, our currency is the American dollar. Okay? Similarly, for our body there, okay, the currency of the body is adenosine triphosphate. We use ATP there, or adenosine triphosphate there, okay, in order to create movement. So here's a example of what an adenosine triphosphate molecule looks like. And I don't need you to memorize this. But what I do need you to understand there is ATP here, or adenosine triphosphate, is used in various different sources throughout our body. Okay? It helps us transmit electrical signals down nerves. It helps fuel muscle action. It helps our body circulate blood throughout the body. It aids in digestion. It aids in different forms of glandular secretions there, okay? And it can help us there create different tissue, okay? One example of this is taking amino acids there, okay? And we can use ATP there, okay, to build up these amino acids together to create protein. So ATP is used in many different situations there in our body. Now, what we do with the adenosine triphosphate there, we use it to create energy, is we break down ATP, essentially split apart the ATP molecule, okay, into smaller parts there, okay, and by breaking it down into smaller parts there, we create energy. And as we talked about previously, if you break down a larger molecule into smaller parts there, okay, that's considered to be a catabolic reaction. Okay? And the breakdown of ATP there is done through a process called hydrolysis. Okay? And we're not going to go into the nitty-gritty details of what hydrolysis is. Okay? But essentially, hydrolysis there is the breakdown of a molecule there in water. Okay? Essentially what happens is with water and ATP there, okay, the enzyme ATPase, okay, which is not shown in the following slide, okay, it creates on the opposite side ADP, adenosine diphosphate, okay, plus a phosphate ion plus a hydrogen ion. Okay, so essentially here, okay, taking three adenosine triphosphate, okay, or a molecule with three different phosphates on it, okay, splits it up into adenosine diphosphate, so two phosphate ions, and then we get that extra third phosphate, okay, now broken off of it. When we look at the chemical reaction in the next slide, okay, is that we've got reaction arrows that point in both directions, okay, meaning we can recreate adenosine triphosphate if we have an ADP molecule, a phosphate ion there, and a hydrogen ion as well. Okay. So resynthesis of ATP is the same reaction in the opposite direction, and it is anabolic. Okay. So breaking down ATP is catabolic, but when we create ATP, okay, this is considered anabolic. So here's an example of this. On the left here, we've got adenosine triphosphate there. And if we break off one of these phosphate ions, okay, by breaking it off, that gives us energy that we can use to fuel movement in our body. Likewise, the opposite reaction is also true. Okay, if we use energy, okay, to add a phosphate ion to adenosine diphosphate or ADP, okay, we can add that phosphate ion on to recreate more ATP. And so our body does this often throughout the body, break down ATP, okay, and then when we get fuel there, okay, we get more energy there, okay, we can use that energy to add the phosphate ion back on and create another ATP molecule, and that ATP molecule there is then sitting and ready and waiting to be broken down again to create more energy to fuel movement. Now here's the important thing about adenosine triphosphate, or ATP there. Only limited amounts of ATP can be stored within the muscles. It would be nice if we could store a whole ton of ATP in our muscles so we could use it to break down, to create energy anytime we need it. Okay. Now, through exercise, training on a regular basis there, we can increase the amount of ATP that we can store in our muscles Unfortunately, it's not enough ATP that we can store there to sustain some form of exercise for any meaningful length of time. Okay? Essentially, they're at the start of exercise or any sort of movement. We have an immediate need to regenerate or recreate ATP molecules there so that we can break them down again to create energy some more. So therefore, since our body doesn't store a whole lot of ATP in the muscle, because storing a ton would be very inefficient there for our bodies there. Therefore, we have three different energy systems that our body uses to resynthesize ATP. Resynthesize is just a fancy term of create or recreate their ATP. So we've got these three different energy systems that are used to recreate ATP there so that we can continue to break down ATP molecules for further movement. And here are three main sources of ATP, okay, aside from the ATP that is stored in our muscles. Okay. We've got the phosphagen energy system, otherwise known as phosphocreatine energy system, also known as the PCR energy system. Okay. Essentially what we do is we take the phosphocreatine molecule, okay, and we use this phosphocreatine molecule there to create more ATP. The second source of ATP is anaerobic glycolytic system, otherwise known as glycolysis, also otherwise known as the lactic acid system. Okay. Now, what this term anaerobic means is that energy is created there without oxygen. So anaerobic without oxygen. And technically, the phosphocreatine energy system is also anaerobic because no oxygen is used as well. Okay. But anaerobic glycolysis, otherwise known as lactic acid system, does not use oxygen there to create ATP. Essentially, what the anaerobic glycolytic system, or glycolysis, it uses anaerobic glycolysis, okay, or anaerobic glycolysis there, okay, using glucose there for fuel to create more ATP. Okay. Now, this anaerobic glycolytic system gets working in high gear there, meaning it's used very rapidly and very often there. Lactic acid can accumulate there as a byproduct of anaerobic glycolysis. And we'll talk about why this actually might be a good thing later on in the PowerPoint slide set. And then the third source of ATP is our oxidative system, okay, otherwise known as our aerobic energy system. So oxidative, oxy, okay, meaning oxygen there. Okay. So energy is produced while oxygen is present. Okay. So again, oxidative system is the only one of these three energy systems that produces ATP there aerobically with the presence of oxygen. Now, here's something important to note, and I will make a star or somewhere in your note set here. Okay. The level of intensity of a movement is related to the rate at which a system can provide ATP there. Okay. So remember that with intensity there, intensity could be how fast something moves. Something's moving faster is considered to be more intense. Okay. If you are lifting a heavier weight there, okay, lifting a heavier weight there, okay, would be more intense than lifting a lighter weight. Okay. If you need a lot of energy very quickly with very little rest in between, okay, that would be a more intense activity than an activity where you don't need a whole lot of ATP very quickly. Now, this is important to note here because the intensity of movement is separate from the amount of ATP that a system can provide. Because some energy systems can provide ATP very rapidly, okay, but they cannot produce a ton of ATP. Versus on the flip side, some energy systems, okay, provide a lot of ATP, but they do so very slowly. Here's one example there. The oxidative system, the aerobic energy system, has a lot more chemical reaction steps in it in order to go through the entire oxidative energy system than does the phosphagen system. Okay? Meaning that the oxidative energy system produces ATP a lot more slowly. Okay? and therefore cannot provide as much ATP for high intensity activity as the phosphagen system. However, the oxidative system can provide a ton more ATP in the long run compared to the phosphagen energy system. And we'll talk about these a little bit more in the coming slides. So start off with the phosphagen energy system. Okay. Here's down here, the second equation there, okay, shows how the phosphagen energy system is used to create more ATP molecules. So we've got an ADP molecule, adenosine diphosphate, okay, and with that there, we combine it with the phosphocreatine molecule. And using the enzyme creatine kinase, okay, we break off this phosphate on the phosphocreatine, okay, we add it to ADP to create more ATP molecules, okay, leaving creatine there kind of just sitting in the body. And once our body is resting there, we can use creatine kinase in the opposite side there. And to this, I apologize. Once we start exercising and we need ATP broken down to create energy, creatine is added to one of the phosphate ions there, okay? And that we recreate phosphocreatine there, okay? And we've got ADP left over, okay? Here's another example of this here, okay? So up here's a summary of what happens when we break down ATP. Break down ATP molecule, okay? Get rid of that phosphate ion, leaving us with the ADP and that phosphate ion. Okay? Over here on the right there shows what happens when we split up the phosphocreatine molecule. Okay? Essentially break down that bond between the creatine and the phosphate ion there, okay? Leaving us with creatine plus the phosphate ion. Okay? Down here on the left side shows the chemical reaction when we use phosphocreatine and adenosine diphosphate to recreate more ATP. So our body needs more ATP, so we can take that ADP, combine it with phosphocreatine, okay, leaving us with ATP and creatine. Okay. Now, in extreme situations, okay, where we need a ton of energy very quickly, okay, and we might not have enough phosphocreatine around to recreate more ATP, okay, we can take two ADP molecules, and from one of the ADP molecules, take off one of the phosphate ions there, okay, and we can use that to create ATP and AMP, adenosine monophosphate, AMP. So 3 phosphate ion or phosphate molecules here versus 1 phosphate molecule on this. So, as it mentioned or showed in the previous slides there, okay, this slide kind of explains there in words what we just showed in the previous slide there. Okay, so ATP can be rapidly resynthesized in 2 ways. Okay, so if I need ATP very quickly, okay, we can recreate it there in 2 ways. So phosphocreatine, which is stored in your muscle there, okay, is broken down by creatine kinase, okay, liberating its inorganic phosphate ion there, okay, essentially taking off this phosphate ion there, okay, and the energy released is used to combine this phosphate ion with ADP to create ATP. Okay, so that's one way we can rapidly recreate ATP. And as I mentioned previously, if in very extreme situations, we can take 2 ADP molecules, which have just been taken off phosphate ions there from 2 previous ATP molecules, and we take off 1 phosphate ion there from one of the ADP molecules to create ATP, okay, leaving us with just AMP left over. Okay. Now the AMP is broken down to produce ammonia, okay, which is not an energy source there. Now again, this phosphocreatine energy system, or both of these energy ways of recreating ATP, the system is very fast, but it only creates a very limited, or there's only a limited amount of phosphocreatine that is stored in the muscles, so it's depleted very quickly. So just like the muscles only store a minimal amount of ATP in the muscles there's only a limited amount of phosphocreatine that is stored in the muscles that we can use for creating more ATP. So therefore, just like ATP stored in muscle is depleted very quickly. Phosphocreatine stored in the muscle is depleted very quickly. Now, because phosphocreatine is limited in the muscle there, okay, the phosphagen energy system can replenish ATP at a very quick rate, high rate there, okay, but it's depleted very quickly, okay, potentially in under 10 seconds there. Okay. If you look at this slide here, if we undergo a very intense bout of exercise and we maintain it, try to maintain it there, we break down all the phosphocreatine that is stored in the muscles very quickly within roughly 30 seconds there. So our phosphagen energy system provides energy mainly for the first 10 seconds of intense exercise, but it can last roughly around up to 30 seconds there. Now, once we start to rest there, we'll gradually recreate phosphocreatine, restore it in our muscles. So while our body is resting, okay, and doesn't need that ATP, or we will recreate phosphocreatine to be used again when our bodies need to move again very intensely. So depending on the severity of the depletion of phosphocreatine, it can take anywhere between 5 to 15 or more minutes to recover our muscular stores of phosphocreatine. So phosphocreatine can be used very rapidly to create ATP, but it takes a little bit of time, 5 to 15 minutes, to restore our phosphocreatine storage spots in our muscles. So again, this is a good summary slide of the phosphagen energy system, and it's something that would star there in your notes. So it's the most rapidly available source of ATP, okay, which means the highest level intensity exercises, okay, it will provide the vast majority of ATP for the initial parts of that exercise. It involves the breakdown of phosphocreatine, okay, but it's limited by the availability of phosphocreatine there in our muscles. We don't store a lot because to store a lot of phosphocreatine would be very inefficient. So as mentioned at the very beginning of this PowerPoint slide set, our body wants to be very efficient. It doesn't want to do any more than it needs to. So only limited amounts of phosphocreatine are stored in our muscles. Okay. It's the main source of energy for exercise lasting up to 30 seconds. Okay. But again, as mentioned previously, at very high intensities, this energy system will basically be exhausted within about the first 10 seconds. But it can be the main source of energy up to 30 seconds. Second energy system, anaerobic glycolytic system. So anaerobic glycolysis there involves the breakdown of carbohydrates to make ATP. So again, as I mentioned previously, carbohydrates was one of our three main sources, okay, of food there that is used to create ATP. And anaerobic glycolysis, okay, can take carbohydrates from two different sources. Number one is we've got glucose in the blood. So when our body ingests carbohydrates there, okay, it breaks down those carbohydrates, and the broken down carbohydrates are glucose, and there is glucose in our blood there, and our muscles will soak up essentially that glucose in our blood and use it there to create ATP. Okay. Also, we have what's called glycogen, okay, which is essentially the stored form of glucose in our body. It's stored in the muscles as well as the liver. Now, anaerobic glycolysis there occurs in the muscle cell sarcoplasm. Think of the sarcoplasm there as the kind of like the jelly, or it's kind of like the liquid substance in a water balloon. So if your water balloon is a cell there, the sarcoplasm is going to be, the sarcoplasm there is the kind of the water that's inside the cell there. Now, unlike the phosphocreatine energy system, which had one chemical reaction to create ATP, okay, anaerobic glycolysis has multiple different chemical reactions, okay, that are used to create the ATP. Okay. So therefore, since the phosphagen system, okay, has only one chemical reaction step compared to anaerobic glycolysis, which has multiple enzyme reactions there, the glycolytic system will be slower to produce ATP. So the anaerobic glycolysis is slower than the phosphagen energy system in creating ATP. However, because there's quite a bit more glucose in glycogen in our bodies, and we can get it through by consuming carbohydrates there, means that anaerobic glycolysis can produce far more ATP than the phosphocreatine energy system. Now, the end result of glycolysis is the production of pyruvate. Okay, and so essentially, one molecule of glucose or one molecule of glycogen, okay, both of those yields two molecules of pyruvate. And we'll talk about what we use with pyruvate in some of the coming slides. So with the end result of anaerobic glycolysis being pyruvate there, okay, this pyruvate can be used two different ways. With lower intensity exercise, okay, think like a easy walk, okay, or maybe doing household chores there. This pyruvate there will be shuttled into the mitochondria, okay, in the muscle cell, and further processed for more ATP. Okay, this is called aerobic glycolysis, okay, and it's used in the oxidative energy system. Okay. Now, at higher intensity levels, essentially we have a buildup of pyruvate in the muscle cell. Okay, and in order to get out of this log jam there, some of the pyruvate is converted into lactic acid. Now, lactic acid kind of gets a bad rap there. So we hear about lactic acid, and we hear about it because that's the burn that we feel in muscle when we perform high-intensity exercise, okay, for a sustained duration there. Okay. What lactic acid is a combination of pyruvic acid, okay, which is used with a pair of hydrogen ions. So essentially, take pyruvic acid there, okay, and you got two hydrogen ions with them. Okay. There are two molecules of lactic acid per one molecule of glucose. Okay, and again, that would make sense there because we get two pyruvate molecules at the end of glycolysis. Okay, we would get two lactic acid molecules there per one molecule of glucose during very intense exercise. Okay. Now, lactic acid gets a bad rap there, but here's the good thing about lactic acid. Lactic acid there is actually used by the heart and the liver are used by the heart and liver there when the heart and liver need energy. So while lactic acid, it's that burn you feel and can cause you to slow down there, your body uses it in the heart and the lineage to fuel the heart and the liver there. So our body actually uses lactic acid, okay, when it starts to be built up there, and it's used by the heart and the liver to try to lower the lactic acid levels. Okay. Number two, by lowering the lactic acid levels, anaerobic glycolysis can continue to function properly to continue creating more pyruvate and more ATP. So again, glycolysis nets two ATP molecules per one glucose. And why I say the term nets there is that glycolysis will use a little bit of ATP, okay, in order to create more ATP. Kind of like if you invest money into the stock market there, you have to invest some money in order to get more money back in the long run. So likewise, glycolysis will use a little bit of ATP to create even more ATP in the future. So if you take the amount of ATP glycolysis creates, and you subtract from the amount of ATP that it actually uses, okay, the leftover there is two ATP molecules are created in net there per one molecule of glucose. So here's a slide there that shows all the different chemical reactions and all the different steps there, okay, that glycolysis goes through in order to create ATP. I don't need you to memorize this, okay? But the biggest thing I want to point out here is look at all the different chemical reactions that are occurring. So because of all these different chemical reactions that are occurring, okay, this means that glycolysis will be a lot slower than the phosphagen energy system. Okay? But on the flip side there, we create a lot more ATP. Okay, and specifically there, okay, notice here, okay, ADP, okay, we create ATP. ADP, create ATP. So 1, 2, 3, 4 ATP molecules are created, okay, from glycolysis there, and we use 2 ATP molecules up here. Notice it shows ATP going or being broken down into ADP. So glycolysis there, okay, taking 1 glucose molecule, we use 2 ATP in it, but then we create 4 ATP out, leaving us with 2 ATP net. So the anaerobic glycolytic system. Again, this is a summary slide. It would something that I would star or make a note of in my notes. It basically fills the gap in energy production between the phosphocreatine energy system and the aerobic energy system. What it does is that it essentially makes it possible to exceed the maximal capacity of aerobic energy system. While our aerobic energy system is nice because it can produce the most amount of ATP, it is very slow compared to the phosphagen or phosphocreatine energy system there. So therefore, anaerobic glycolysis there is used there to create additional ATP that our body needs during maximal exercise. Anaerobic glycolysis involves the incomplete metabolism of glucose there. Okay. So it's important to know there's a difference between anaerobic glycolysis versus aerobic glycolysis. Okay. Anaerobic glycolysis means the incomplete breakdown of glucose versus aerobic glycolysis will break down glucose there all the way efficiently there. Now understand there, remember though that all glycolysis is anaerobic, okay? But we can use carbohydrates in both our aerobic energy system and our anaerobic energy system, specifically anaerobic glycolysis. Our anaerobic glycolytic system is limited by the accumulation of lactic acid. So too much lactic acid, okay, will slow down anaerobic glycolysis, which means our heart and liver there uses the lactic acid there for energy and also to get rid of that excess lactic acid. Finally, anaerobic glycolysis is the main source of energy during exercise that lasts between 30 seconds and 2 minutes. So versus the phosphagen energy system is the main source of energy for the first 30 seconds, okay? Starting at second 30, going all the way up to 2 minutes upon the start of exercise. Anaerobic glycolysis is the main source of energy. What's important to note here is between 30 seconds and 2 minutes of exercise, is our phosphagen energy system still working, still providing with some ATP? Yes, it is, but it's a lot less compared to the amount of ATP being provided by our anaerobic glycolytic system. Third energy system, or oxidative system. Okay, oxidative meaning using oxygen. Now again, the oxidative energy system is our only energy system that uses oxygen to create ATP. Okay. Also, it is the only energy system that can use all 3 macronutrients. It can use carbohydrates, fats, and proteins to create ATP. So compare that to the phosphagen energy system. The phosphagen energy system cannot use carbohydrates, cannot use fats, cannot use proteins there to create ATP. Compare this also to glycolysis. So glycolysis can only use carbohydrates to create ATP. It cannot use fats, it cannot use proteins there, okay, to create ATP. The mitochondria in our muscle cells is the location, okay, where the ATP is created in our oxidative energy system. Okay? And in the mitochondria, there are 2 different parts of our oxidative energy system. We've got the Krebs cycle, otherwise known as the citric acid cycle. This creates some of our ATP. And we also have the electron transport chain in our mitochondria there. The electron transport chain also creates ATP. So here's an example of a cell there, okay? In our cell there, okay, we've got mitochondria, okay? And in our mitochondria, we've got our citric acid cycle, okay? And we've got the electron transport chain. So these 2 things create ATP in our mitochondria there, okay? And we'll talk about a little bit later on there, okay, kind of what happens there with these two different cycles there, the citric acid cycle and electron transport chain, when creating ATP. Now, up top here, okay, this is glycolysis, okay. Glycolysis there is again, it occurs in this cytosol, okay, in that jelly-like substance there, that water-like substance there in the cell, okay, and we can create some of our ATP there, okay. Now, part of this glucose molecule, or glycogen molecule up here, okay, is that we get our pyruvate, and the pyruvate there from glycolysis there is used in our citric acid cycle to create more ATP, okay. For example here, okay, see how ADP goes to ATP, okay. So citric acid cycle creates ATP. Now additionally, okay, citric acid cycle also creates some hydrogen ions, okay. So it creates some hydrogen ions, and these hydrogen ions, okay, are combined with other molecules there, and these hydrogen ions then are shifted to our electron transport chain, and our electron transport chain will use those hydrogen ions, okay, to create even more ATP. So there are 3 steps, okay, if we are aerobically breaking down carbohydrates there to create energy, okay. The first step occurs in the muscle cell sarcoplasm, okay. Aerobic glycolysis occurs in the sarcoplasm there, okay. But again, as we talked about previously, glycolysis, the entire process is anaerobic there. But we use our carbohydrates, okay, in the sarcoplasm there. Glycolysis happens, creates some of their ATP, okay. But then in the mitochondria there, okay, the Krebs cycle creates some ATP, and the electron transport chain creates ATP. Specifically, the Krebs cycle uses pyruvate from glycolysis to create more ATP. The pyruvate specifically is converted into the molecule acetyl coenzyme A, okay, otherwise abbreviated as acetyl-CoA, and that is used in our Krebs cycle there. The electron transport chain, okay, will use hydrogen ions that were created, leftover byproducts from the glycolysis and from the Krebs cycle. They are used in the electron transport chain to create even more ATP. So here's a summary there of the usage of ATP and the creation of ATP there when we break down carbohydrates there throughout the process of aerobic energy system. Now, what's important to note here is not so much the exact numbers. I don't need to know that there, okay? But what I do want to point out there is how much more energy is created, okay, by breaking down carbohydrates aerobically. So if you can see here, up top here, okay, 2 ATP is the net amount of ATP that is created from the breakdown of glycolysis anaerobically. So through glycolysis, 4 ATP are created, 2 are used by glycolysis there, netting us 2 ATP total when glycolysis is used to create energy. However, okay, through the aerobic energy system, the citric acid cycle and electron transport chain there, okay, these are used to create even more ATP aerobically in the presence of oxygen, meaning we create a lot more ATP in total there through the aerobic energy system. Okay. Couple summaries of the carbohydrates there, okay. The exact numbers aren't important, okay. What's important to note there are the certain trends there, okay. So essentially 686 kilocalories, which is kind of confusing, but kilocalories essentially are just calories, okay, that you see in the nutrition labels on food substances there, okay. So 686 calories there per molecule are released from glucose, okay. 263 kcals or calories there are stored as adenosine triphosphate. Okay. Now through the aerobic metabolism or aerobic breakdown of glucose, okay, this is 38% efficient, okay, meaning that we have a lot fewer byproducts from aerobic breakdown of glucose compared to the anaerobic breakdown of glucose, okay, because anaerobic breakdown of glucose or anaerobic metabolism there, okay, is only 2 to 21% efficient. Okay? So essentially the missing energy, okay, that we lose out from the breakdown of these different molecules of glucose there is lost as heat, okay, which we use heat, this lost energy there, to maintain our body temperature at rest, okay, and also raises body temperature during exercise. Okay? So the breakdown of carbohydrates is not completely efficient, but it's a lot more efficient to break down carbohydrates there aerobically compared to anaerobically. The third macronutrient that we break down to create ATP there are fats there. Okay? And we can only break down fats in the aerobic energy system. Okay? Now, fats have a lot more, or they're a lot more complicated. They got a lot more bonds between the different building blocks there. Okay? So therefore, the process of breaking down or metabolizing fats is a lot slower than the process for breaking down carbohydrates. Okay? But the breakdown of fats can produce a ton more ATP than can breaking down carbohydrates. So triglycerides there, okay, is essentially the fat form or the way that our body stores fat in cells there. Okay? But triglycerides there, essentially storage fat there, are broken down, okay, by the enzyme lipase to produce free fatty acids, otherwise known as FFAs. Okay? And free fatty acids are moved around in the blood to the muscle cells when we need energy. Okay? In the mitochondria there, okay, along with the Krebs cycle and along with the electron transport chain, okay, which uses breakdown parts of fats there to create ATP, we also go through the process of beta oxidation. What beta oxidation is, converts free fatty acids into acetyl coenzyme A. And that acetyl coenzyme A there, again, is going to be used by the Krebs cycle to create even more ATP. So by breaking down fats there, okay, and specifically the free fatty acids, breaking those down there in the mitochondria there, we've got 3 different sources of ATP there, okay, through the process of breaking down fats for ATP. So here's our diagram there, okay, showing the citric acid cycle and the electron transport chain, which you talked about previously. Okay? But third there, okay, a breakdown of the triglycerol molecule, okay, so triglyceride there, okay, being the storage form of fats there, okay. So if we break down that triglycerol molecule there, okay, we get glycerol and 3 fatty acids. The glycerol there, okay, is used through glycolysis there to create even more ATP. Okay? And the 3 fatty acids will go through beta oxidation. Essentially a bunch of different cycles through these 3 fatty acids there to create even more ATP, create even more ATP, create even more ATP. Okay? And to create even more ATP, we produce a ton more ATP in the long run by breaking down fats compared to breaking down carbohydrates. So if you were to summarize breaking down fats there, okay, to activate the breakdown of fats there requires 1 ATP, okay, but each pass there, okay, of breaking down more and more of that those triglycerides there, okay, each pass there going through beta oxidation there, okay, produces 17 ATP, okay. Specifically, 5 ATP is created from beta oxidation, and 12 ATP are created from the citric acid cycle and the electron transport chain. Okay? So creating a ton more ATP there, okay, and breaking down even further there, okay, the last breakdown of those 3 different fatty acids there, okay, does not require beta oxidation to occur, so it produces only 12 ATP. Okay. Now the total amount of ATP that is produced depends on how long each fatty acid chain is. Okay, but the bottom line, okay, as we showed here in this previous slide, okay, the exact number is not important. Just know that it's a lot more ATP, okay, that's created from the breakdown of fats compared to breaking down of carbohydrates. Now, the third macronutrient source for energy is proteins. Now, breakdown of proteins is definitely or not a significant source of ATP for most activities because we want to use protein for other functions in our body, specifically to maintain muscle tissue. But in extreme situations, for example, if you are starved for a long period of time, okay, for example, if you're out in the middle of nowhere and you can't find food and you need to survive there, your body will start breaking down muscle in order to continue to fuel your body. Okay? Now, if it is used in breakdown, for example, those extreme situations, okay, proteins are first broken down into amino acids. Okay? Essentially, amino acids are like the Lego blocks or the building blocks of proteins. Okay? This breakdown of proteins is known as deamination. Okay? Amine, okay, kind of looks like amino. Okay, so deamination is the breakdown of proteins. Now, these amino acids, broken down proteins, can be converted into glucose and acetyl coenzyme A. Okay, and therefore we can use glucose and acetyl coenzyme A. Okay, that have been created or converted from these amino acids, and those can be used in glycolysis. Okay, and used in the other oxidative paths there for breakdown of carbohydrates and fats, like previously. So here's a diagram there. Okay, we got our muscle cell. Okay, inside our muscle cell, we've got our mitochondria. And the big thing I want to point out here is that where these different sources, food sources there, which parts of glycolysis and the oxidative energy system, where do different parts of these broken down substances, where do they go? Okay, what you'll notice there is that parts of protein, okay, are used in the process of glycolysis. Okay, so if we break down amino acids, parts of it are used in, or let me rephrase that there. Okay, so parts of proteins there are broken down when they're broken down into their amino acids. Some of it's used to create pyruvate. Okay, now pyruvate is the end product of glycolysis as well, but pyruvate there is not, or the protein there is not used in glycolysis. Okay, essentially, protein broken down creates additional pyruvate, which again is used in our in the mitochondria with our oxidative energy systems. But protein itself is not used in glycolysis. Also, take a look at fats there. Okay, so fats there, okay, parts of it, specifically the glycerol there, okay, the glycerol is used in, or it uses additional substance, okay, that additional substance can be used by glycolysis, but glycolysis itself does not break down fats. Okay, fatty acids can be used by our aerobic energy system. Okay? Carbohydrates there undergo glycolysis, and parts of it will be used by aerobic energy system as well. But basically there, okay, again, a reminder that our aerobic energy system can use all three sources of foods: carbohydrates, fats, and proteins. Versus glycolysis, okay, can only use carbohydrates directly there to create ATP. Proteins and fats are not directly used by glycolysis. So, oxidative energy system summary. Okay, this involves the complete metabolism of glucose. We break down glucose completely there. Okay, the oxidative system is also used to break down fats and proteins. Now, the important thing about the oxidative system, with all the different chemical reactions that are occurring, a lot more, even more than glycolysis there, the oxidative energy system may not be immediately available to supply additional energy. Okay. Maximal energy demand also may exceed the maximal capacity of the oxidative system to produce ATP. So, for example, if I sprint very fast for a minute, okay, that the amount of energy needed to sprint as fast as I can for a minute will exceed the amount of energy that the oxidative system can provide. Or not provide there. It's by sprinting as fast as I can for up to a minute there, it needs too much ATP too quickly. And our oxidative system can only can provide that amount of ATP, but it cannot provide it quick enough. So we need to rely there on our anaerobic energy systems, our phosphagen system and glycolysis there, to produce the additional ATP needed to sprint as fast as I can for a minute, that our aerobic energy system is not fast enough to provide quick enough for. The oxidative energy system is also the main source of energy at rest and also during exercise bouts that last longer than 2 minutes. Now this slide here, what's important to note here, okay, our immediate energy system is like our phosphocreatine energy system. Short-term energy system, that's glycolysis. Long-term energy system, that's our aerobic energy system. Now, all three energy systems are always active at all times, no matter what activity you are performing there. Okay. However, which one is the main source of energy depends on the duration of the activity and the intensity of the activity. Okay. But all three energy systems, no matter how long our exercise bout is occurring, and no matter how intense that exercise bout is occurring, all three energy systems are used by the body to fuel movement. Now, the important thing to note on this slide here is that as the duration of our exercise bout increases from 10 minutes, 20 minutes, 30 minutes, 40 minutes, 50 minutes, okay, the percentage of total energy, okay, that is created by our energy systems shifts. Okay, as you can see, at the very start of an exercise bout there, our main sources of energy is going to be our anaerobic energy systems. Okay, this is highlighted in blue. But as that exercise bout continues, okay, we run out of our anaerobic energy system sources. Okay, so they provide very minimal exercise or minimal ATP there for exercise the longer the exercise bout goes. Versus aerobic energy system, again, is very slow because it has many different chemical reaction steps. So it doesn't provide nearly that much ATP relative to the amount created by our anaerobic energy systems at the beginning. But as it gets kicked into high gear, and as our anaerobic energy systems are not able to continue producing as much ATP, our aerobic energy system becomes the primary form of ATP production there, the longer the exercise bout goes. Here's another example highlighting how these different energy systems interplay with each other. If I do a 10-second sprint, 50% of the ATP that I need to perform this 10-second sprint there, 53% is created by the phosphagen system. And again, the exact numbers aren't important. What's important is the relationship between the numbers. So phosphagen energy system is the main source of energy for a 10-second sprint, followed by anaerobic glycolysis and the aerobic energy system, being creates the minimal or the least amount of ATP for the 10-second sprint. However, a 30-second sprint, which is longer there, notice here that anaerobic glycolysis, okay, becomes the main source of energy. Phosphagen energy system has decreased from 53% to 23%, and aerobic energy system is now providing a greater percentage of the ATP. And this trend continues the longer the exercise bout lasts. So this slide kind of summarizes our sources of energy. Okay, so this would be something I'd definitely star somewhere in your notes. At rest, the main source of energy is the aerobic energy system. But is glycolysis being used? Yes, it is. Is the phosphagen energy system being used to create ATP? Yes, it is, but it's very minimal. Main source of energy is going to be the aerobic energy system. Okay? And specifically at rest there, okay, our body likes to break down roughly 2/3 of the macronutrients, or 2/3 of macronutrients coming from fats there, and 1/3 of the macronutrients being broken down coming from carbohydrates. For exercise of short duration, less than 30 seconds, main source of energy is the phosphocreatine energy system. Okay? The lactic acid system, otherwise known as glycolysis, and the aerobic energy systems gradually provide more and more ATP as the exercise bout gets closer to 30 seconds. Intermediate exercise duration there, 30 seconds to 2 minutes. The main source of energy is going to be the lactic acid system, otherwise known as glycolysis. Early on in this exercise bout there, phosphocreatine is going to provide a good percentage of the energy, but it will continue to drop off as we get closer to 2 minutes. Aerobic energy system provides the additional ATP, especially as we get closer to 2 minutes of exercise. For prolonged exercise, greater than 2 minutes, the main source of energy is going to be the aerobic system. Okay? Early on, again, in past 2 minutes, phosphocreatines can provide more energy, but it will continue to drop off. Lactic acid will also continue to drop off. In addition there, with prolonged exercise, if exercise intensity increases at certain points beyond 2 minutes, for example, if I'm thinking I'm running a marathon there, and the last 400 meters of that marathon, I want to sprint as fast as I can so that I can finish the race in a good time. By increasing my pace there, the last 400 meters or so there, that produces more, or it requires more ATP than what the oxidative energy system can provide. So the lactic acid energy system will provide that additional ATP there, okay, to make yourself run a little faster there at the end of the race. What this slide there is just essentially highlights, okay, are the storage parts of different forms of the 3 different macronutrients, okay, and where do they go and where are they used by our different energy systems. So we got our triglycerides in the adipose tissue, okay, so essentially triglycerides are our fats being stored. Protein that is stored in the muscle and the liver, and glycogen that is stored in the muscle and the liver. But then again, this slide there essentially highlights what happens to these 3 different substances and how are they used in our body. So 3 different macronutrient usage there, okay? So carbohydrates, okay, and protein intake are strongly regulated in our body, okay? We will store excess carbohydrates, okay, or we will build, or with proteins there mainly, we will build muscle tissue, okay, as needed there, okay, and we'll burn the rest right away. Okay? So a lot of what we consume there in forms of carbohydrates and protein, a lot of it does get catabolized, okay, meaning broken down there, and some gets stored, okay. So the protein there is gonna, I should say carbohydrates there will get stored as fat there, okay. Protein will first be used to repair muscle, okay, but once that protein already has been used to repair all the muscle it needs, okay, excess protein can also be stored as fat, okay. But again, because protein is mainly used to build muscle, repair muscle, okay, it is rarely used as energy, but in extreme situations, it can be used as a form of energy. But oftentimes we'll ignore protein use or protein consumption in terms of creating energy. Now, fats there are not very well regulated, okay? Not being well regulated, meaning that we have an almost unlimited capacity to store fats. And our body does this for a survival mechanism. So our body never wants to starve. So if it consumes an excess amount of calories there, okay, whether it be carbohydrates, fats, or proteins there, okay, we will store that in our body as fats there, okay. And essentially, we have almost an unlimited capacity to store fats, okay? And that's one reason why you see people that are very large, very overweight, if due to many different factors, but oftentimes not exercising enough, eating too much, and possibly maybe some hormonal imbalances that cause their metabolism to drop significantly. So if you want to burn fat during exercise there, okay, it is important that we exercise in a fasted state, okay? So meaning that if you, during the actual exercise bout, if you want to burn fats there, okay, do exercise in a fasted state. Because if you exercise in a fasted state there, it means that we have minimal amounts of glucose that are floating around in our bloodstream, and we will use our muscle glycogen storage pretty quickly there. And when we use those two different sources of energy, we're left over with needing to get energy from other sources. So we'll break down fatty tissue, okay, and break down that fatty tissue there to create more ATP to maintain our exercise bout there. Now, one thing to note there, okay, we also, as I mentioned in the previous slide, we break down fats more at rest there, okay, compared to during exercise. Because again, breaking down fats is very complicated, it's very time consuming. But we can also break down fats there at rest. So that's why it's important to manage how many calories you're consuming throughout the day, okay? So that we don't consume too much, and therefore the excess is stored as fat there in our body. Now, what's the order of usage in our body? Okay, we will first use carbohydrates, followed by protein, followed by fats there. Okay, and what I mean by this here, okay, is that this typically is meant during like essentially intense forms of exercise. So we'll first use carbohydrates there. Okay, we will then use any excess proteins because proteins are broken down more easily. Okay, and fats are the hardest to break down during intense exercise there. Now, alcohol actually is a form of exercise or is a form of energy. We can actually break down alcohol there to create ATP. But it's not recommended, number one, because if you're exercising when you have a lot of alcohol in your body, that's not a good thing. It's probably unsafe. Okay. Number two, in your body there, the reason we break down alcohol first is because alcohol is a poison. So just like we need to get rid of poison as quickly as possible, we need to break down that poison very quickly, the alcohol there, so that we can get it out of our body. Okay. But again, for the most part there, carbohydrates and fats are used for energy. Okay. The use of protein is negligible because again, we would want to mainly use protein to repair muscle. Okay. Use of alcohol for energy is very minimal because again, we shouldn't be exercising when we have a ton of alcohol in our body. That's all I got. If you have any questions, let me know. Have a good day.